All right, so in our do now, we drew the structural formula for this ion. We decided that there were 6 electron groups for octahedral electron group geometry. You'll see where electron group geometry comes into play today with hybridization. We know its molecular geometry is square planar, and don't forget when you have an ion, you need the brackets with the charge on the outside. Okay? So hopefully after the weekend with Monday as well, you feel better about drawing and shape. And we'll address both in the second half today when we do your lab, where you'll be drawing compounds and constructing them with molecular model kits, which is very fun. Okay? We're going to talk a little bit about polar and non-polar compounds, a little bit about dipoles. And again, the POGO packet here is really complementary to this. I thought it was a great explanation. Some of the things that I thought were always a little fuzzy were really explained well in the packet, so it is definitely worth your time. You've seen a lot of this before. I'll go through some of the basics with you. For example, in a polar molecule, we know that the electrons in the bond are shared between 2 atoms, but in a polar molecule, they're not shared equally. So the atom with greater electronegativity draws the bonding electrons to itself more, and it develops a partial negative charge. For example, hydrogen chloride. Hydrogen is of lower electronegativity. It's 2.2. Chlorine's probably about 3.2. If you need this information, it will be provided to you. Chlorine is in fact 3.2. So the difference in electronegativity here is 1.0. So this is a polar bond. Your dipole would be established pointing in the direction of the more electronegative atom. You usually slash the back half, and that's the signal as well that this is partial positive and this is partial negative because it draws the bonding electrons toward it. We know chlorine also has 3 lone pairs. You may be given dipole moments. You won't be asked to calculate them, so don't worry about it. If you have a polar molecule, the molecule will have a non-zero dipole moment. Dipole moment is often abbreviated with this U. It looks like micro, and the unit is a capital D for debye. Other than recognizing that this is a dipole moment, there's not much else you're going to have to do. You don't have to calculate it. If you have a nonpolar molecule, the dipole moment is 0. So if we want to determine whether a molecule is polar or nonpolar, there are 2 considerations we typically have to address. The first is we want to see if there are polar bonds in the molecule. No polar bonds, no lone pairs on a central atom, very simple, the molecule's nonpolar. I'll give you an example. If you have polar bonds, you also sometimes need to look at the shape of the molecule, because sometimes, say it again, I'm on the wrong screen. What else is new? That's Casey's job. So 2 things you want to consider. You want to consider whether the bonds have dipoles, and you want to look at the molecular shape. And we're going to look at several scenarios here. A lot of them you would have seen at the honors level. There's just one new piece here, and then we'll do a few examples. C says a molecule with all nonpolar bonds and no lone pairs of electrons on the central atom must be nonpolar covalent. Again, this is at the honors level. It's exactly what I did in honors a half an hour ago. So this goes with C. If you have methane, C to H bonds are nonpolar. That is something I think you should commit to memory. It will be handy. So if you just have hydrocarbons with C and H's, those are nonpolar. That's why, for example, hexane, octane, things like that, those are all nonpolar molecules. They're not water soluble. Methane, the C to H bond is nonpolar covalent. If all the bonds are nonpolar covalent and there are no lone pairs on the central atom, the molecule is nonpolar covalent. Yep.
What was the range again for like the value?
Less than 0.5 is nonpolar covalent. Between 0.5 and typically 2.1 is polar.
Okay.
But they're not going to ask you that. They may say which is more polar. If they give you the values, you could figure that out. All right. In D, it says if,
And it's higher, is it more polar?
correct. The greater the electronegativity difference, the more polar the bond. D says if only one bond is polar, the molecule is polar as it is asymmetric. And we'll explain the symmetric versus asymmetric concept. I think I'll do, no, it doesn't matter. I'll do D over here. So for example, if you had methyl fluoride, the C to H bonds, polar or nonpolar? Anything that is a nonmetal hooking to a fluorine will be polar. Fluorine's the most electronegative atom, electronegativity value of 4.0. The next most electronegative atom is oxygen at 3.4. So anything hooking to fluorine that's a nonmetal will make a polar bond. So what you've got here, keep in mind the dipole points in the direction of the more electronegative atom. So it goes this way. You have one dipole, nothing can cancel it out. This is a polar bond. The molecule is polar covalent. All right, so case 2. In E, it says the presence of a single lone pair of electrons on the central atom results in a polar molecule because the molecule is asymmetric. It doesn't have symmetry. For example, ammonia. The N to H bonds happen to be polar. And this is where the packet I thought was outrageously good. It explained a lot of things that sometimes are murky. The lone pair as well has a slight dipole, so there's no cancellation of dipoles here. If you ever have a structure in which there is one lone pair on the central atom, the molecule is polar covalent. Your reasoning here is that the molecule is asymmetric. And last year I argued with a couple of teachers in the county on this because I said that pH3 would be polar. And they said, no, P to H is all nonpolar. But I said, no, the dipole there's a slight dipole with the lone pair. And they're like, no, no, no. But if you look at that packet I gave you, it showed that a single lone pair will result in an asymmetric molecule, so it's polar. So I'm going to stick with it. I got this really long explanation from this guy at FAU, but I can share it with you, but it's so complicated.
But pretty much if there's a lone pair of electrons with like three things
If you
on.
have trigonal pyramidal, it will be polar. If you have bent, it will be polar. But you cannot say, and this is where you'll see it, this is where AP goes a little bit higher. So if you have trigonal pyramidal or bent, you're going to have a polar molecule. You know that water is a polar molecule. That's why waxes and things don't dissolve in it. They're nonpolar. So if you ever have trigonal pyramidal or bent, it is going to be polar covalent. Just be careful, because there's going to be two shapes in which you have lone pairs on the central atom that can be nonpolar. So that's where it's tricky, and I'll show you those too. All right. So again, if you look at all the rules, everything is the same in honors through F1, but then there's F2, which takes it to a higher level because we don't do expanded octets in honors. So F, if all the bonds are polar, examine the shape to determine whether the dipoles cancel. The dipoles will cancel if the molecule is perfectly symmetrical. Shapes like linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. Those make for perfectly symmetrical. Also the funky linear and square planar, and I'll go over those two in F2. But in F1, this is the same thing as you saw at the honors level. So in F1, if you had something like carbon tetrafluoride, this is as if there's a child in the mall throwing a temper tantrum and 4 adults are coming to try and get this child away somewhere safely. If one parent pulls on an arm, another parent pulls on an arm, a sibling pulls on a leg, another sibling pulls on a leg, if they're all pulling with equal force, the kid doesn't go anywhere. So what you have here is the dipoles are equal but opposite in terms of their direction, and as a result, the dipoles cancel. So here we have polar bonds. We said anything that hooks to a fluorine that's a nonmetal is going to be polar covalent in terms of its bond. But the molecule is nonpolar covalent because the dipoles cancel in this symmetrical structure. Now, one question that was in your packet is this molecule is nonpolar covalent, so the net dipole is 0. But if you had sulfur tetrafluoride, that is a polar covalent molecule. Why would sulfur tetrafluoride be polar covalent? What's the difference between these two? Still polar bonds. Around what? Right. So in this one, and this is where if you did a lot of drawing over the weekend, and you'll get more in today, you would see that this structure is not tetrahedral, but rather that is a seesaw. Okay? So this is polar covalent. This molecule is asymmetric. Polar bonds and asymmetric make for a polar molecule.
That's because of the lone pair.
And so now the positioning of these does not cancel the dipoles. In addition, this is a small dipole as well. And when you construct this, you'll see it better.
So since that one's asymmetrical, it's positive.
Yes.
That's the reason.
Yep. Asymmetric molecule with polar covalent bonds is polar covalent. Here's the AP link. It says, be very careful with linear. This is the funky linear, AX2E3. That's 2 atoms attached, 3 lone pairs. And square planar, AX4E2. 4 atoms attached, 2 lone pairs. As these shapes do have lone pairs and yet still illustrate perfect symmetry, they would be nonpolar provided that the atoms attached are the same and there's no charge. If you have an ion, it's not polar or nonpolar, it's ionic. And some of the kids hit the bottom on that one on an AP exam one year, so be careful. So this is the AP link right here. I'll draw these two for you. Be careful with that. All right, so let me give you the examples on F2. So if you had xenon difluoride, the fluorine atoms here do line up with xenon in a linear fashion. And then on the xenon, there are 3 lone pairs. So this is a linear molecule. And here, you do have a non-polar covalent molecule for the same reasons we mentioned here. The molecule is symmetric and the dipoles cancel. The two dipoles here and here cancel, and then those guys cancel because they're equal but opposite. So you're going that way, and then that way and that way. And your packet did a tremendous job on this in terms of explaining net dipole. It really did a good job.
So it'll be nonpolar.
This is a nonpolar covalent molecule. You find something quite similar with xenon tetrafluoride because you have xenon attached to 4 fluorine and 2 lone pair. So this is square planar, and what you see here as well is this is a symmetric molecule and the dipoles will cancel. So this one also is a nonpolar covalent molecule for the same reasons we discussed. They love to ask these.
So those are the exceptions, right?
That's the 2 times where you can have lone pairs on a central atom but have a nonpolar covalent molecule.
Can you what would be the reason? Like what caused
The dipoles, right?
Why is it nonpolar covalent?
Like what would you say for the reason?
The molecules are symmetrical, resulting in cancellation of dipoles.
Because they're all pulling, right? Or when they're all pulling. Are they pulling with the same strength?
Yep.
Or,
Well, not these 3 are each equal but opposite. This is making a trigonal planar design, if you will, and then that's linear across, so those are canceling. Yep. Okay, so let's take a look at this question. And one of the girls stopped in during lunch asking a lot of questions, and she's like, well, how do you know this is linear, and how do you know this is this, and how do you, I said, well, you have to draw it first. She said, you have to draw it first? I'm like, yes, you have to draw it. You know, some of you are going to know because you've seen these before, but the best approach is to draw.
Mm-hmm.
Draw, draw, draw.
And then you just go through.
Some of these you know because you've seen so much. Nitrogen gas. N is doubly or triply bonded to itself. Triple. Anytime you have a triple bond, your shape is linear. In addition, if you only have 2 atoms, and just like in kindergarten where you connect the dots, you get a line. So that's linear. Anytime you only have 2 of the same atom, it has to be nonpolar because the electronegativity difference is 0, exactly. Methane we did. You know that C to H bonds are nonpolar. No lone pairs on carbon in almost every case except carbon monoxide and cyanide ion. So this would be nonpolar. BF3, be careful with this one. This is not like ammonia. Is boron an exception to the octet rule? Yes, it is. Boron forms 3 bonds, no lone pairs. Now let's think about this. That is a polar bond. No lone pairs on the central atom. Is that a symmetrical molecule?
Yeah. No lone pair.
It is. Your symmetrical molecules are the ones with no lone pairs, provided that the atoms attached are pretty much the same or have grossly similar electronegativities.
So they're non-polar?
That would be nonpolar covalent. The molecule's symmetrical, so the dipoles cancel. That's the wording you're looking for. Short and sweet. Hit the key words. All right. Now we have seen SO2 before, but again, if you didn't practice drawing, it's going to come back and bite you. You should have tons of sheets of drawing. When you physically cannot draw another structure, that's a good sign. We talked about sulfur dioxide because sulfur dioxide exhibits, starts with an R, resonance. The bond order between S and O would be 1.5, right? Okay. What's its shape? Bent. Anytime you have one lone pair on a central atom, the molecule is polar because the molecule is asymmetric. You've got it.
And the angle is 118,
118. Why is it slightly smaller than the 120?
because the lone pair pushes the angle.
Why?
It has its own dipole.
The lone pair repels
Uh,
more than
as
a bonding pair, which compresses the bond angle. A lone pair repels more than a bonding pair, compressing a bond angle. Also, I will just want to make sure this point is clear because you know you're going to see it. Explain to me why the bond angle in water that is an HOH is slightly smaller than the HNH. There's 2 lone pairs, so if you just write that, are you getting credit?
No, 2 lone pairs are
Okay, so
push against each other.
the lone pairs repel more than the bonding electrons, and the lone pairs repel each other, further compressing the bond angle. Okay? The lone pairs repel more than the bonding pairs, and the lone pairs repel each other, further compressing the bond angle. So that's the key there. All right. The last one we did, let's look at sulfur. Did I show you the video, sulfur? Did you see the talking, the deep talking? Yeah, you did, right? It was funny. I looked up because the kids are like, can we order this? It's $352 for a canister.
Wow.
I know. Just to have fun.
What is it used for? Besides that,
That's a really good question.
why would it be so expensive?
I don't know. Actually, all of the gases were very expensive, probably because it's compressed, so that you have to pay for the canister too, which may not be cheap, but I don't know why it's so much. All right. So anytime you have 6 of something, it's pretty easy, right? And that's the most electron groups you can have, so there won't be any lone pairs on sulfur. So this is a gimme. You know that each fluorine would have 3 lone pairs, so this would be, because the molecules, symmetric, the dipoles, you got it. So good. All right. In terms of what's left, I'm really going to simplify it because I don't think you'd ever be asked to explain it. It gets very, very complicated. your book goes into bonding and anti-bonding orbitals, it's just out there. It's more for organic chemistry, so it's too much. So we're really going to keep it simple, very simple. In terms of atomic orbital overlap, when orbitals get near one another, they overlap. Leave it there.
Is it? Free self-claim.
Hybridization.
That's it. Oh my God.
Hybridization. When you have those atomic orbitals overlapping, they will often blend together to form orbitals that have intermediate properties. For example, you can look at this here. All right, so you're going to mix the atomic orbitals to form special orbitals for bonding. If you had an S and 3 P's, they will blend intermediate energy and form an sp3 hybrid. If you have an S and 2 of the 2 P's, you'll form an sp2. If you have an S and 1 of the p orbitals, you'll have sp. Keep it very, very simple. It looks something like this. Who cares? Because it's too complicated. I'm going to slide right here and make it really, really simple. Where the electron group geometry is going to come into play is right here with hybridization. Super simple. If you have 2 electron groups, you have sp hybrid orbitals. They'll say, what's the hybridization? Anytime you have the linear molecular geometry, not the linear weird molecular geometry, you have sp. Let's take a look at the 2 examples. Beryllium, you will recall, is an exception to the octet rule, and so it forms 2 bonds, 2 lone pairs. This has a linear shape. You have 1, 2 electron groups. The hybridization is sp. If you had hydrogen cyanide, you have 1, 2 electron groups. The hybridization is sp. If you have trigonal planar electron group geometry, this includes trigonal planar. It includes the bent with 2 atoms attached, 1 lone pair as well. You are going to have sp2. For example, we know boron trifluoride has 3 electron groups, and it's sp2. And I'll show you a trick to remember that as well. When you have 2 electron groups, S1, P1, 1 plus 1 is 2, 1 plus 1 is 2. Here, 1 plus 2 is 3, 1, 2, 3 electron groups. This structure as well, how many electron groups? 3, sp2. And back to sulfur dioxide. If they give you sulfur dioxide in May, you better draw it so beautifully, or I'm going to have a temper tantrum. 1, 2, 3. So these all have 3 electron groups. 1 and 2 is 3, sp2. And your lab will go into hybridization more. By the time you get done with that, you won't have to study hybridization. All right. The other one you have to know for the quiz, the exam, and the AP exam is sp3. So if you have tetrahedral electron group geometry, this can be tetrahedral molecular geometry. It can be trigonal pyramidal geometry. or it could be bent, where you have the 2-2. In each of these cases, how many electron groups do you have? Either 4 bonds, 3 bonds in a lone pair, or 2-2. This is all sp3. Okay? Now the lab does do sp3d, sp3d2. There's really not too much to it. The AP exam doesn't require it anymore, so you won't see it on the quiz or test, but I did have it in the lab because I wanted you to construct these more complex structures. So for example, I'm going to be lazy on my lone pairs on chlorine. How many electron groups? 5, sp3d. 1 and 3 and 1 is 5. And if you had SF, sulfur hexafluoride, because you wanted to talk crazy, you'd have sp3d2, adding all the superscripts, you get 6. Hybridization. You want to try one?
Yeah.
Okay. Let's do this one. Now, well, you don't have to be able to do this anymore. You want to do silicon tetrachloride?
Sure.
All right. Read it carefully. I want the hybridization scheme. I want if it's polar or nonpolar. And the best approach is to draw it. I'll do it too. This one's easy. Right, JJ? Hi, Christian. We miss you.
Not really.
That's not nice. We're going to get to do lab soon. So much fun.
Is this gonna be due after the break?
Yeah, it can be. I mean, it really should be due Monday, Tuesday, but I think you guys will be super uptight. Well, we'll when we shut this off, we'll figure that out, because the only problem is if you really delay it, then it's going to interrupt your next chapter. So we'll agree on something and make it work. All right, so we do it? Did we do it? What'd you get? What'd you get? Oh, yeah. I did it like that. That's an I. Did you get what I got? That's a really good sign. The only thing I think kids mess up with hybridization is like water. Water's sp3. That, for some reason, they have trouble with.
I see the polar bonds and the subterranean are equal. So, like, that's like
Yeah, that's not going to cut it. So a little tighter than that. That's why. And see, I know sometimes it sounds like we're chanting answers out, but I think you'll remember them when the time comes. All right, last thing. And this too, we're going to keep it really, really simple. This is not something you're going to have to explain, and it's very, very, very complicated. I can show you a little bit. But again, these get very tricky. So a sigma bond, it says an electron pair is shared in an area centered on a line running between the atoms. And a pi bond forms double and triple bonds by sharing electron pairs in the space above and below the sigma. And I'll show you how to determine that very simplistically. Well, they'll show it to you here. This is pretty cute.
The carbon-carbon double bond in ethylene consists of a sigma and a pi bond. An sp2 hybrid orbital on one CH2 unit of ethylene overlaps with an sp2 hybrid orbital on the other CH2 unit to form the carbon-carbon sigma bond. Now we use a side-on view to show how the remaining unhybridized p orbitals on each CH2 unit overlap to form the carbon-carbon pi bond.
Now that's a little tricky the way it's shown, so we're really going to simplify that.
Was the second part the two pairs of hydrogen?
See, what I don't like with that pi is it's sort of like a half a pi, half a pi. It's not a pi and a pi. So let's keep it simple. I'll show you what I mean. I have some examples here. We'll take a look at one of them. I threw this into your notes after the fact because I threw it on your quiz and it looks intimidating, and I want to show you how easy it is. All right, before we do that, let's say, and I'll just make any generic structure here. Okay. Cranky wanky. Okay, let's say you had something like that. Okay? Everywhere you have a single bond, you have a sigma bond. Sigma, 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 sigma. Everywhere you have a double bond, you have one sigma. Everywhere you have a triple bond, you have one sigma, which is the middle one. If you have a double bond, you have one pi.
On top of the sigma?
It doesn't, whatever was the sigma, the other one's the pi. In the triple, it's more obvious because the top and the bottom ones are pi. So if they asked you to count your sigmas, sigma is abbreviated this way, pi as such. You'd have 1, 2, 3, 4, 5, 6, 7 sigmas and 3 pi's. All right? So, because I didn't want to sit there and start drawing structures in, I found structures just to pull. And this one is kind of funny because it's cocaine. This is the first thing kids usually ask how to do when they enter chemistry. I don't know why. But let's say you had this structure. If I asked you how many pi bonds there were, you would look where all the doubles are, right? Because there are no triples. So what looks really hard will take you 3 seconds. 1, 2, 3, 4, 5. Okay? Which one? This is not.
It's not too long.
I don't
No.
understand the
What's
names.
that?
It almost looks like an upside down boat conformation. When you get into 6-ringed structures, they twist, and I'm really going back to organic chemistry, and this is like 20-something years. But what I do remember is a boat and a chair conformation. That looks like the upside down boat, but I could be wrong. It's been a long time. I'll look in my Orgo book and check. I just don't remember.
Okay, so this one just had more.
All right, the other thing you could do here, and this is a little tricky, I'd have to print it, but what I did on your quiz to make life easy Oxygen has a single bond, single bond. If I had a lone pair here and a lone pair in here, because I would, what'd be the hybridization with respect to the O? sp3, you got it. And I made it very easy, like wherever the points meet, this is a carbon. So if this is a carbon with a single, single, and a double, how many electron groups? 1, 2, 3. So that would be sp2. And that is as easy as those questions are on the quiz. So you may see an intimidating structure. Don't let it intimidate you. Very straightforward questions, okay? And then on the end right here, there'd be a lone pair. So that would be sp3 or sp2? sp3. And that shape would be 3 things attached, 1 lone pair. Trigonal, pyramidal. And that's all she wrote. I don't think you need to know geometric isomerism anymore. We're going to let it go. Everything else in the chapter is no longer addressed in AP. And so we will switch over to the lab.
I'll try to study because I'll forget.
Yep.
The nitrogen what we just said, and then the hybrid orbital will be sp3.
So then this does the same.
Yeah, we said that.
And then the structure though would be
Pyramidal.